So in this problem, we're going to find the partial sum of s sub 10 of the series 1 over n to the fourth power, where n goes from 1 to infinity. And we're going to estimate the error of using s sub 10 as this partial sum to 10 as an approximation to the series. So the first thing I'm going to do is find that s sub 10. And so s sub 10 would be equal to, well, if n was 1, it would be 1 over 1 to the fourth power, plus n being 2, 1 over 2 to the fourth power, plus 1 over 3 to the fourth power. And I'm not going to write them all out, but we're going to know that they're there, all the way up to 1 over 10 to the fourth power. And when I did this, I used my calculator. You can use Google Sheets, however you want to try to get this estimate as fast as you can. So I actually got the decimal values of each of these terms, every term, there's 10 of them, out to at least 5 decimal places. And so when I did this, I got an approximate amount for the sum of 1.08204. So I'll leave that to you to find, to match up that number using whatever method you choose to. And then this error of this estimate. And so what we're saying, using it as an estimate, so if I were to continue on into, infinity, so n is, so it's 1 over 1,000 to the fourth power, and I continue on and on and on, there's a certain finite sum. And so it has this, this certain finite sum, which later in the problem, we're going to get to see exactly what that finite sum is. But right now, we're saying, okay, we don't know what it is, but there is some number, it's this finite sum, and I only calculated 10 terms of this. Was that getting me close to it? Are all the rest of the terms small enough it's a negligible amount, or, what I consider negligible? So let's find the error of just using the first 10 terms summation as an approximation to the series. So that's where this remainder estimate integrals will come in with this inequality. So n plus 1 to infinity, our f of x is 1 over x to the fourth. And then that's dx less than or equal to r sub n less than or equal to the integral of n to infinity of 1 over x to the fourth dx. So we're going to use this remainder estimate for the integral test. And then I'm going to let n equal 10 because that's what I went out to on my partial sum. So this, if n is 10, then this becomes 11 to infinity of 1 over x to the fourth dx is less than or equal to the remainder. So remainder at 10 is r sub 10, less than or equal to 10 to infinity of 1 over x to the fourth dx. So I just let n be 10 everywhere. And now I notice I have these two integrals that have 1 over x to the fourth as a function in there. So I'm going to work on just finding the antiderivative of that. So I'm just going to do the indefinite integral of 1 over x to the fourth dx, recognizing that that's x to the negative 4. So if I do some scratch work on the side, x to the negative 4, if I add, then that's going to be x to the negative 3 all over negative 3, which can be written as negative 1 over 3x cubed. So the antiderivative is negative 1 over 3x cubed. That's going to be my antiderivative for the function, and so I'm going to utilize that. And my limits, since I have this improper integral going to infinity on the left and right side. So on the left side, it's limit as a goes to infinity of this negative 1 over 3x cubed going from 11 to a. And on the right side, it's the limit. So let me draw an arrow so you can see. It's this left side and this right side that I'm working on right now. Limit as a goes to infinity of negative 1 over 3x cubed from 10 to a. And then write this out. I get limit as of negative 1 over 3a squared. And this is 8 goes to infinity And this is minus the limit of negative 1 over 3 times, a cubed, excuse me, 3 times 11 cubed as a goes to infinity, but that's just a constant on the right. And so this limit will equal 0 on the left. This negative sign, so the subtraction sign and the negative sign make a positive, so this becomes 1 over 3 times 11 cubed, which is approximately equal to 0.00025. And we'll do that for the right side as well. So we have the limit. So again, don't go throwing infinity to the third power or anything there. That doesn't make sense. A to the infinity of negative 1 over 3a cubed minus the limit as a goes to infinity of this constant, negative 1 over 3 times 10 cubed. Same thing's going to happen. This limit is 0, and on the right you get a positive 1 over 3 times 10 cubed, and that is approximately equal to 0.00033. So what we found, so let's kind of wrap this up in a nice little bow here. The remainder of that partial sum, so r sub 10, is less than or equal to 0.00033, less than or greater than or equal to 0.00025. So not too shabby. So we're within almost 4 decimal places there. And so at most, the error would be like 0.0004. Or you could even say 0.0034, because that would be above the number on the right. That's at most what it's going to be. So that gives us the error of using, so it's not too bad. It's within a few decimals using that partial. Now for the next piece, we're going to use the lower and upper bound to find a better estimate of this s. And so we're going to use this lower and upper bound. And again, we're going to let n equals 10. So I'm going to go ahead and plug in my function and my 10s everywhere. So my formula becomes s sub 10 plus the integral of 11 to infinity of 1 over x to the 4th dx less than or equal to s less than or equal to s sub 10 plus the integral of 10 to infinity of 1 over x to the 4th dx. Now that's just me using that lower and upper bound formula and plugging 10s in everywhere. Now the thing to notice here is I've already calculated s sub 10. Way up here, s sub 10 was this 1.08204. And I've also already calculated those integrals with the limits starting in 11 and 10. The first one is put 0.00025 and the second one is 0.00033 respectively. So I can plug in all of those decimal values I've already gotten. So you'll notice now I have 1.08204 plus 0.00025 is less than or equal to s, is less than or equal to this 1.08204 plus 0.0003. And that gives me 1.08229 is less than or equal to s, and that's less than or equal to 1.08237. So my s is between there. And just like any two numbers when you have to find the midpoint, so if we want to go between like 4 and 10, if I want to find the midpoint value, right, that would give me a good estimate, like kind of an average between the numbers there. You add the numbers and divide by 2. And so if I wanted between 4 and 10, I'd get 14 over 2 is 7. That would give me the midpoint. I'm going to do the same thing with these two numbers here. I'm going to get the midpoint by adding them up and dividing by 2. And when I do that, those two lower and upper boundaries, I get 1.08233. And so this is my new estimate for the finite sum s. And looking at that, they want you to say, okay, what is the error on that though? At most, what would it be? Not the exact error, but at most, what would it be? And looking again at my picture from 4 to 10 I have over here, where I said, you know what, let's pick 7, it's in the middle. The most of your error is going to be half that amount from your midpoint out to your boundary. If you're calling your midpoint your estimate, then that most your error is going to be half that. And so the way we would get that is we would take like 10 minus 4, whatever that distance is, divided by 2, and that would give us 6 over 2, that would be 3, right? That's that distance. again, we're going to do the same thing with these numbers, but I'm going to do big minus small. So 1.08237 minus 1.08229 and divide that by 2. And I get approximately equal to 0.00004. Now what I want to point out is this, at most, is what the error is. And if I go by using that midpoint as an estimate, if I go up to my previous part, at most the error estimate was this 0.0004, but this one is at most 0.00004, so it's even better. And so now we're gonna say, okay, let's check these out and see how they compare. And so when I used S sub 10 as an approximation to S, then I got that was S is approximately equal to 1.08204. And then when I used my remainder estimate instead, the remainder estimate, the less than or equal to all the integrals, that I got S is, and the midpoint, S is approximately equal to 1.08233. And then we're given, by looking at some previous information in the book, that from Euler we have that the series, he actually found what the exact sum is, and it's pi to the 4th over 90. Now this pi to the 4th over 90, when I get a decimal approximation of that, that's 1.082323. So this is the exact sum. Here's a decimal approximation out to 6 decimal places, and look at how close my second one using the remainder estimate was. So that's not too bad at all. I think that's pretty good. And so we have one more piece to the puzzle. So the last piece is to do something where they want to see how many terms would you have to go to get within a certain error bound. Like you have a restriction, you have to have some kind of accuracy. So they want to be within 0.00001 of the actual finite sum. So they'll word this as find a value of n, or how many terms are required. So that's saying how far do you have to go out on your partial sum, how many terms, to get within this accuracy. So that's how they'll word it sometimes. And we're going to use that remainder estimate, the right-hand portion. R sub n is less than or equal to the integral n to infinity of 1 over x to the 4th dx. And we want that to be less than the 0.00001. So we're going to use some information we already discovered. So in completing this improper integral of n to infinity of 1 over x to the 4th dx, I bring in the fact that I know the antiderivative is negative 1 over 3x cubed, and I find the limit of that a to infinity, and the bounds are n to a. And when I plug all that in, taking the limit from a to infinity of negative 1 over 3a cubed, that will equal 0, and that's minus the limit of a to infinity of the constant negative 1 over 3n cubed, because n is treated as a constant here. And so we get this positive 1 over 3n cubed. So that's what we want. 1 over 3n cubed is less than 0.00001. And then just using my math, I have 1 over 3 times that 0.00001 is less than n cubed. I take the cube root of both sides, and when I punch this into my calculator with this cube root of 1 over 3 times 0.00001, I get 32.18, and then just doing some rearrangement because n was on the greater than side, n has to be greater than 32.18. So you'd have to have at least 33 terms to get within that 0.00001 accuracy for the sum of the series.